AI distillation, also called knowledge distillation or model distillation, is a technique for transferring knowledge from a large, complex model, called the teacher, to a smaller, simpler student model. The goal is to build a student model that performs nearly as well as the teacher, but uses fewer computational resources, less memory, and consumes less energy. This approach makes powerful AI capabilities more efficient and practical for real-world deployment. Let us see a comparison of large language model, in short LLM, and small language model, in short SLM. This slide compares the token price of OpenAI's O1 large language model with DeepSeek R1. The cost per million tokens for DeepSeek R1 is about 30 times lower than that of OpenAI O1. Knowledge distillation, the process used here, has existed for over a decade. However, it gained widespread attention when DeepSeek released a reasoning model whose performance was nearly comparable to OpenAI's, but at a fraction of the cost. This demonstrates how knowledge distillation can drive efficiency without significantly sacrificing model capability. Here we see a benchmark comparison of OpenAI's distilled models. The top left image compares the cost per million tokens for GPT-4o and its distilled version, Mini. GPT-4o Mini is 16 times cheaper than the larger GPT-4o model. The bottom left image shows that this cost reduction comes with only a 6 percentage point drop in benchmark performance, from 88% to 82% on MMLU. On the right, the green arrow highlights this trade-off: significant cost savings with only a minor decrease in performance. This dramatic expansion of the price versus performance envelope with distillation is one of the key reasons for the commercial success of LLMs. The bottom row shows examples of various models distilled from the larger models on top. Note the model architectures of student could be entirely different from the teacher. Distillation has become an industry-wide phenomenon. The slides provide a sense of variation in the number of parameters from teacher model to student models of Llama family of LLMs by Meta. The teacher model is 2 trillion parameters, whereas student model is only 109 billion parameters. It is important to understand the characteristics of each of the model types, which make them suitable for some use cases while limiting other. Let's talk about teacher model characteristics. These are large models having vast amount of knowledge. Being large makes them slow and costly during inference, and hence are usually unprofitable for commercial usage. They are more suited for research and development purposes of artificial general intelligence, AGI in short. Hence their source code and trained weights are kept proprietary and rarely open-sourced. It is usually the small distilled model that are open-sourced. Distilled student models are smaller, resulting in lower latency and reduced cost. This makes them highly profitable for commercial deployment. They're also ideal for academic use and public evaluation, including open source and marketing purposes. Their narrow, task-specific skills are well suited for specialized deployment in multi-agent frameworks. Their specialization allows each agent to excel at a defined role, boosting the overall system's efficiency. Due to their speed and small size, these models are practical for edge AI and IoT devices, such as smartphones and drones. Their ultra-fast response times also unlock real-time applications, like fraud detection. Here's a simple framework to help decide if distillation is appropriate for your use case. This 2x2 matrix plots required precision on the vertical axis and task generality on the horizontal axis. The green area in the bottom left highlights where distillation works best: tasks with low precision requirements and a narrow domain. Examples include sentiment analysis, entity extraction, and opinion mining. Distilled models are well suited for these tasks, delivering cost-effective performance without the need for extremely high accuracy or broad generalization. Tasks that fall in the yellow quadrants either require higher precision or broader general capabilities. Examples include classification, copywriting, summary generation, and support chatbots. For these types of tasks, distilled models provide okay performance. Distillation is a practical option here, but results may not match those of larger, more specialized models. Tasks in the red quadrant require both high precision and broad general capabilities. Examples include accurate translation and open domain Q&A tasks, such as those performed by ChatGPT. Distilled models are not suitable for these demanding, high-reasoning applications. They tend to perform poorly in scenarios where both depth and breadth of reasoning are required. Distilled models play a critical role in making the agentic AI framework more efficient and cost-effective. Agentic AI works by breaking down a complex goal into multiple subtasks. Most of these subtasks require less reasoning power than the original overarching goal. Distilled models are ideal for handling these smaller, specialized subtasks. Meanwhile, the few tasks that demand high precision and advanced reasoning are handled by large, more powerful reasoning models. This approach allows the majority of work to be completed by smaller, cheaper models, significantly reducing the overall cost. By combining distilled and large models, agentic AI frameworks achieve greater cost efficiency than relying on a single large reasoning model for every task. Hence, in ideal case, AI agents in the agentic AI framework would look like many distilled small models and few large models. Let's peek under the hood to understand how distillation is performed. First, there are a few key design choices that needs to be made to set up distillation. The first key question is, at what stage of the LLM training pipeline should distillation be applied? Option 1 is pre-training, which we discussed earlier. This is what Llama 4 does. Option 2 is post-training. DeepSeek applies distillation at this stage. Option 3 is to apply distillation during both pre-training and post-training, as done by Gemma 3 by Google. This flexibility in applying distillation enables researchers to balance efficiency and performance based on the chosen stage. A next key question when distilling LLMs is how knowledge is transferred from the teacher model to the student model. There are two main approaches: proper distillation and behavioral cloning. Proper distillation involves carefully transferring both reasoning ability and underlying generalization patterns to the student model. This can be performed only when access to both teacher and student model is available, which is usually when both models are owned by same company or teacher is open source. In contrast, DeepSeek's approach is better described as behavioral cloning. Here, the student model learns to imitate the observable behaviors of the teacher, but may not fully capture the deep reasoning skills. This performed when source code and weights of teacher model is not accessible. As shown in the illustration, models like Gemma 2.3 and Llama 4 Scout Maverick come from proper distillation, while Llama 3.1 and Qwen 2.5 follow the behavioral cloning path. This distinction affects how well the student model generalizes and adapts to new tasks. Let's look at these types of distillation in detail. This slide explains proper distillation in LLM training. Imagine the teacher model is already fully trained. At each training step, we take a sample document and have both the teacher and student predict the next word in a sequence. For example, when predicting the word mat, both models generate a probability distribution across the entire vocabulary for what the next word could be. The teacher's output is called a soft label. It provides probabilities for multiple possible words, not just a single correct answer. The student model's goal is to match its probability distribution to the teacher's soft label as closely as possible. The student's weights are updated to minimize the gap between its predictions and the teacher's output, effectively transferring knowledge from teacher to student. Now let's look at what DeepSeek R1 calls distillation, but is more accurately described as behavioral cloning. In this approach, the teacher generates a dataset, and the student is trained using standard next word prediction. However, unlike proper distillation, the labels here are hard labels. They assign 100% probability to a single correct word, e.g. mat, and 0 to all others. There's no dark knowledge or nuanced probability information passed from teacher to student. The student is simply imitating the teacher's final output, not learning the reasoning behind it. This method is much simpler and does not require access to the teacher's probability distributions, soft labels, making it possible even when the teacher model is a black box. However, behavioral cloning passes less information to the student and typically leads to less effective training compared to proper distillation. Let's now see the steps of distillation. There are two major steps. First is extraction, and second is distillation. In first step of extraction, training data is sampled from the teacher model, and in second stage of distillation, the student model is trained using this training data. Let us understand each of these steps. The first step of knowledge extraction could be performed in several ways. There are 6 different ways knowledge can be extracted. Let's see those. Here are the 6 ways in which training samples can be generated using the teacher model. In next few slides, we'll see each of these with concrete examples. First way is to have the teacher model label some unlabeled data sets and basically generate a correct answer. For example, sample question is, what is the capital of France? And teacher answer is, Paris. This question and answer pair serves as training data. The second way is to have the teacher model generate variant of the data from a demonstration to expand the data set. For example, multiple examples of addition is generated. The third way is to have the teacher model synthesize a collection of data given a topic. For example, a topic of movie review is provided with task to generate positive review example pairs. The fourth way is to feed some data into the teacher and extract the teacher's internal knowledge features such as data distributions or logits and use those meta-information as the training target. For example, probability scores of all the vocabulary is extracted. The fifth and the last way is to have the teacher generate feedback on the students, generations which can be corrections, preference rankings, or elaborations of challenging samples. In this case, student and teacher work together iteratively to receive feedback. This is more helpful for RL-based training. These are most of the methods used for knowledge extraction. After knowledge extraction, the next is distillation, in which student is trained on the dataset. There are 4 popular methods of distillation. Let's discuss each of these methods. Here is the list of 4 methods used for distillation. We have discussed how supervised fine-tuning and reinforcement learning and ranking optimization works earlier. The concept is exactly same. Let's briefly double-click each topics. In supervised fine-tuning, the same prompt is used on both teacher and student. The student's output is compared against the teacher's output, and loss function is used to update model weights of the student. This method works best with the labeling knowledge extraction method discussed earlier. The second is matching probability distribution of answer options between the teacher and student model given the same prompt. This is achieved by minimizing the callback LIBOR, in short KL, divergence loss function between the PDFs of the two models. The divergence is used to update the model weights of the student until the divergence is minimized. Next is RL-based distillation. Like in RLHF and RLAF, the student model is fine-tuned twice. First, the reward model is trained using teacher. In second step, the trained reward model is used to again train the copy of student model using RL algorithms to improve its policy. Next is ranking optimization technique. In this, student generates several outputs and teacher ranks them and provide the feedback. In this process, the student learns which is the best response. These techniques of knowledge distillation can be mixed and matched. They are also performed iteratively until desired accuracy of the student model is achieved or plateau in accuracy is reached. Knowledge distillation process is computationally expensive. Consider, for example, the training dataset has 8 trillion next token prediction tasks. The vocabulary size is 128,000. Hence, the number of soft labels across all examples is 10 power 18. If we stored all of them in precision floating, as shown in the top image, that would be too large for even today's supercomputer. Hence, in practice, full distribution is not used. Any soft labels other than the 256 are zeroed out. This leads to soft label of around 10 power 15 values. This is more manageable, but still massive, so it's likely these soft labels are computed on the fly and then immediately discarded. Congratulations, we have completed 5th major milestones of our journey in the agentic AI landscape. We just saw the topics on the right bottom of the AI landscape. Feel free to pause and take a quick break. Don't forget to come back because we will discuss pre-training. It is where the LLM learns to reason, is up next. Pre-training is the first phase in training a large language model, LLM, where the model learns broad language understanding from massive text datasets. The process involves giving the model huge volumes of text and having it predict the next word in each sequence. This pre-trained model forms the basis for later fine-tuning and task-specific adjustments. Interestingly, the way intelligence grows during pre-training is well understood and follows established scaling laws. Let's first explore what these scaling laws mean. The scaling laws of LLMs reveal how a model's performance improves as we increase model size, the amount of training data, and compute resources. These laws allow us to anticipate the benefits of scaling up, providing confidence when making decisions about investing in larger and more expensive training runs. Scaling laws illustrate in this image how AI system performance improves with increases in data, model size, or computational resources. Pre-training scaling was the first key principle. See at the bottom left, it shows that increasing dataset size, model parameters, and compute power led to predictable gains in intelligence and accuracy. This law drives the development of massive transformer models, mixture of experts architectures, and distributed training techniques. Post-training scaling goes further. It enhances pre-trained models for specific tasks or domains using methods like fine-tuning, distillation, RLHF, RLAIF, best-of-n sampling, and synthetic data augmentation. Think of pre-training as school and post-training as specialized job training, making models more efficient, accurate, or tailored to the problem at hand. Best-of-n sampling and search methods allow a model to consider multiple outputs or decision paths, then select the most promising one, Synthetic data can be used to improve a model's handling of rare or edge cases. In earlier sections, we have discussed various post-training techniques. Third law is test time scaling, or long thinking, which takes place during inference. Instead of generating a one-shot response, the model reasons through multiple steps, allocating more compute to arrive at better answers. Examples include chain-of-thought prompting, majority voting over multiple samples, and searching through a tree of possible responses. In earlier sections, we have discussed various test time scaling techniques. These three scaling laws, pre-training, post-training, and test time, together define how modern AI can achieve greater intelligence and adaptability for real-world applications. Let's now dive deeper into pre-training scaling laws. These laws are derived empirically. Pre-training scaling laws show that model intelligence and accuracy reliably improve as we increase dataset size, model parameters, and compute. This relationship follows a power law. Each time we scale any one factor, data, model size, or compute, the performance improves in a predictable, mathematically defined way, but only up to the point where another factor becomes the bottleneck. For optimal results, all three elements must be scaled together. This power law trend is why research can confidently project future gains from larger models, more data, and greater compute. As a result, ever-increasing computing resources are needed to fully realize these improvements in model training. This slide illustrates how the main factors driving AI intelligence are all increasing at exponential rates. Model size is doubling each year. Training dataset sizes are expanding by 2.6 times annually. Compute power is growing at an even faster rate, 4.6 times year over year. Together, this exponential growth across all three dimensions is driving exponential growth in intelligence of AI LLMs. This slide highlights key breakthroughs driving exponential growth in model scaling. In model size, mixture of experts, MOE architectures, such as DeepSeek's 256 expert model, enable more efficient scaling by activating only a subset of experts per token. For training data, as available real-world internet data is used up for training, synthetic data offers a promising path to further expand training datasets. Under compute, large-scale infrastructure projects like Stargate in the US and UAE, with over $500 billion invested, are rapidly increasing available compute power for AI. The momentum of innovations in model architecture, synthetic data, and compute infrastructure is expected to continue. This could drive exponential growth of AI factors, unlocking even more powerful models in the future. Let us now briefly discuss the mixture of expert model, MOE, at very high level. So what is MOE model? Mixture of experts, or MOE, is a widely used architecture that enhances transformer models by leveraging multiple specialized experts. This diagram illustrates the core differences between standard transformers and MOE architectures. The main distinction lies in the decoder block. A traditional transformer uses a single large feed-forward network in each block. In contrast, MOE replaces this with several smaller expert networks. During inference, only a subset of these experts is selected and activated for each input. This selective activation makes inference more efficient in MOE compared to standard transformers. Although MOEs have a larger total parameter count, only a portion of the parameters are used at any time. As a result, MOE models achieve faster inference despite their increased size. DeepSeek R1 and Mixtral 867B by Mistral AI are two famous LLM that is based on MOE. This slide shows the parameter count for the Mistral mixture of experts model, which has 8 experts, each with 7 billion parameters. At the bottom left, you see the total number of parameters is 46.7 billion. However, for any given token, only a few experts are active. This means the number of parameters actually used during inference is just 12.8 billion, as shown on the bottom right. Because of this, the model can scale up in size and learning capacity without increasing inference latency linearly. MOE models therefore expand the size versus latency trade-off, allowing scaling of larger models with less compromise on latency. Congratulations! We have completed most of the milestones of our journey in the agentic AI landscape. We just saw all the topics marked in green curly bracket of the AI landscape. Feel free to pause and take a quick break. Don't forget to come back, because next we'll discuss governance. This is critical for building trust in agentic AI and making sure its power is used responsibly.